Hello, my name is Eric C., a physicist working on the graphene-based interfaces for neural applications, or GIN project, at Jyväskylän University's Nanoscience Center. In nanotechnology, engineering, physics, biology, chemistry all begin to run together, and the lines between the disciplines blurs. This is why, despite having a formal training in physics, I'm working on this project with the chemistry department. Mind-machine interfaces, or more specifically, machine-neuron interfaces, the ability to send and transmit information from nerves to electronic devices and back, sounds like the stuff of science fiction, but such devices already exist today. For example, the cochlear implant takes sound, transforms it into electrical impulses, and then transmits that to the cochlear nerve. Improving these devices will allow for strong advancements in medical technology. It will allow us to help restore cognitive function or mobility when nerve damage has occurred. It will allow us to directly connect computers to nerves. However, the currently existing machine neuron connections have a variety of issues. One of the largest among them is the fact that the way they are fabricated makes them much stiffer than the surrounding tissue, so that the tissue flexes more easily than the metal used to make the machine neuron connection. This means that as time goes on, the friction between the two can cause cellular damage in the local area and lead to scarring and long-lasting damage, which reduces the usefulness of the implant. To develop these next-generation machine neuron interfaces, our group is turning to modifying graphene. Graphene is a lattice of carbon atoms networked together to form a single sheet that is one atom thick. This gives it a surprising degree of flexibility, but also graphene is quite strong and it can conduct electricity. This makes it an ideal candidate for a biosensor and machine neuron interface. And indeed, graphene has already been used to make biosensing devices. By combining this with another technique developed at Jyväskylän University that allows for the chemical modification of graphene via a laser, we hope to build the next generation of machine neuron interfaces. My part in this project is on the fabrication side of things, making the test chips and helping measure them. We have designed our setup so that our chips are compatible with standard HDMI connections. We can connect them to our measurement device simply by slotting them in to an HDMI cable. This allows us to use off-the-shelf parts and makes it very easy to standardize our measurement procedures. Our first goal is to fabricate a chip that will measure pH, or how acidic or basic something is, taking that data and transforming it into electrical signals. This is a somewhat simple goal, but it is a perfect initial first step as proof of concept to launch onto more difficult attempts. This also gives us a good starting ground to troubleshoot our own experimental setup. Since it's relatively straightforward, we can more easily tell what's not working when something doesn't work and adjust our plans accordingly. What I do each day can vary dramatically depending on where we are in the fabrication process, because it is a multi-step, multi-day process. Some days I'm in the clean room for hours. Some days I've set something up to run overnight because it's a process that is primarily automated but will take a long amount of time, and I don't want to hog all the time on a piece of equipment. Some days I'm staying quite late overnight, making some last-minute changes to something so that other people can make measurements or do other steps of the process the next day. And some days, because I have to hand these samples off to another group, and then wait for them to hand them back to me, some days I don't have a lot that I have to get done. So I find other ways to make myself busy. I'll read papers or go over previous data. As an experimentalist, what you do from day to day will change dramatically over the course of a project, both based on how the experiments are going and how you've decided to modify your experiments, following where the project takes you.
Moi! Mun nimi on Annika ja olen jatko-opiskelija kemian laitoksella. Mä on kotoisin Saksasta, mutta nyt olen jo asunut Suomessa 2 vuotta. Minä olen aina kiinnostunut luonnontiedosta. Koulussa mun lempiaihe oli ensimmäiseksi fysiikka. Vain lukiossa ymmärsin, että kemia on kiinnostava ja kiva aihe, josta haluaa tietää lisää. Lukion jälkeen opiskelin kemiaa Berliinissä Humboldtin yliopistossa. Maisteriopintoni aikaan tulin Jyväskylän työharjoitteluun kemian laitokselle. Mä tykäsin Jyväskylästä paljon ja halusin tulla takaisin, kun maisteriopiskeluni oli valmis. Nyt tutkin Lappassa, teen laskennallista kemiaa tietokoneella ja opitan uusia opiskelijoiden labrassa. In the lab, I'm working on a small molecule activation project with main group element compounds. Small molecules, I guess, is like hydrogen, nitrogen, carbon monoxide, or carbon dioxide. Catalysts in the industry often use transition metals to activate those small molecules, but the transition metals are often rare and expensive, and also very often they're toxic and environmentally dangerous. In the small molecule activation project, we try to use main group elements to form compounds with organic ligands, which have interesting reactivities towards those small molecules. So those compounds consist of organic ligand, which is shielding and protecting the main group element. And main group elements we use are from group 13 to group 15, for example, aluminium, germanium, or antimony. In the lab, when we are working with those air and moisture sensitive compounds, we need to use a special kind of technique, which are called Schlenk techniques. In the fume hood, we have a Schlenk line, which consists of 2 glass tubes with connecting valves. One of those glass tubes is for argon, for inert gas, and one of them is for vacuum. So our glassware also have connecting valves, and with pre-dried solvents we can then do air and moisture sensitive synthesis. All our air and moisture sensitive compounds are stored in the glove box, which is a box filled with argon or nitrogen. And if you want to take something out or put something in, you have a chamber which you can put your stuff in, and it needs to be cycled about 3 times with argon and vacuum to make sure there's no contamination of air or moisture. In addition to the work in the lab, I also work on computational chemistry. I'm studying the same complexes I synthesize in the lab computationally, and from the computations I get a lot of insights how those complexes actually react with small molecules. Part of my work as a PhD student is also to teach the new students how to become the chemists of tomorrow. I like this part a lot because I can show them important concepts and give them an insight into the everyday work life of a chemist. In the first year, lab course, we familiarize the students during qualitative and quantitative experience with essential concepts like making a solution with a known concentration, weighing solids, titration or reflux. Jos en ole töissä, mä tykkään olla metsässä mun koirapenun kanssa. Kotona mä pidän myös leipomisesta ja nölmisestä.
Tervehdys kaikille! Minun nimeni on Elina Sievänen ja työskentelen orgaanisen kemian yliopiston lehtorina. Orgaanista kemiaa kutsutaan usein myös elämän kemiaksi. Orgaanisessa kemiassa tutkitaan hiiltä sisältävien yhdisteiden rakenteita, ominaisuuksia, koostumusta ja reaktioita. Orgaaniset molekyylit koostuvat usein hiilestä ja vedystä, mutta niissä saattaa olla mukana myös muita alkuaineita, kuten happea, typpeä ja fosforia. Minun oma tutkimukseni keskittyy lähinnä bioorgaanisiin molekyyleihin ja niistä steroideihin. Steroidit ovat elimistössämme vaikuttavia aineita, jotka toimivat siellä hormoneina. Niitä käytetään myös solukalvojen rakennusaineina ja hermosolujen pienjahaarakkeiden myeliinitupen rakennusaineena, minkä lisäksi ne toimivat myös tärkeinä aineina ruoansulatuksessa. Steroideissa on usein toiminnallisia ryhmiä, joita voidaan muokata. Minun tutkimusryhmässäni minä ja opiskelijani pyrimmekin muokkaamaan näitä steroidimolekyylejä niiden toiminnallisten ryhmien kautta siten, että valmistamme molekyylejä, jotka voivat itsejärjestäytymisen kautta muodostaa materiaaleja, joita voitaisiin mahdollisesti käyttää lääketieteessä ja farmakologiassa, esimerkiksi lääkeaineiden kohdistamisessa ja lääkeaineiden kontrolloidussa vapauttamisessa. Kun olemme valmistaneet uusia molekyylejä, meidän täytyy myös selvittää niiden rakenne. Yksi menetelmä, jota voimme käyttää molekyylien rakenteiden varmistamiseksi, on ydinmagneettinen resonanssispektroskopia eli NMR-spektroskopia. Siinä näyte laitetaan ulkoisen magneettikentän vaikutuspiiriin. Tämän seurauksena atomiytimien spinit suuntautuvat magneettikentän mukaisesti. Seuraavaksi näytteeseen kohdistetaan toinen magneettikenttä, joka on voimakkuudeltaan alkuperäistä magneettikenttää huomattavasti pienempi. Se on myös oskilloiva magneettikenttä. Tämän magneettikentän saa aikaan radiotaajuinen pulssi. Kun tämä pulssi päättyy, spinit palaavat takaisin lähtötilaansa ja tämä saa aikaan muutoksia alkuperäisessä voimakkaassa magneettikentässä. Nämä muutokset tässä alkuperäisessä magneettikentässä indusoivat virran vastaanotin käämille. Kun tämä virta muutetaan analogisesta digitaaliseksi ja sille tehdään matemaattinen Fourier-muunnos, saadaan lopulta NMR-spektri, josta voimme saada selville, minkälaisia erilaisia ytimiä meidän molekyylissämme on, kuinka monta niitä ytimiä siinä on ja kuinka nämä ytimet ovat suhteessa toisiinsa molekyylin rakenteessa. Näiden lisäksi NMR-spektroskopian avulla voidaan tutkia myös molekyylien kolmi- ja neliulotteisia rakenteita sekä tarkastella molekyylien välisiä vuorovaikutuksia. Koska olen yliopiston lehtori, kuuluu työhöni tietysti paljon opetusta. Opetan NMR-spektroskopiaa sekä aineopintojen että syventävien opintojen tasolla ja sen lisäksi opetan myöskin orgaanisen kemian laboratoriotöitä aineopintojen ja syventävien opintojen tasolla. Olenkin siitä onnekas, että saan opettaa niitä asioita, joita myöskin tutkin, joskin tämä on melko yleistä yliopistoissa. Eli meillä monet opettajat opettavat juurikin niitä asioita, joista ovat itse kiinnostuneet ja joita itse tutkivat. Tykkään työssäni erityisesti siitä, että saan oppia joka päivä jotakin uutta. Ja myöskin siitä, että meillä on täällä hyvin monikulttuurinen ja monitieteinen työyhteisö, joka käsittää myöskin meidän opiskelijat. Opiskelijoiden kanssa vuorovaikuttaminen on yksi työni parhaista puolista. Ja toivonkin, että pystyisin kouluttamaan kemian alan asiantuntijoita, jotka ovat varmoja itsestään, hyviä esiintymään ja myöskin pystyvät löytämään aina tietoa niihin kysymyksiin, joita heille työelämässä esiin tulee.
Hello, my name is Gerrit Groenhoff. I'm originally from the Netherlands and I'm now working as a professor in the Department of Chemistry. I became a researcher mainly because I'm interested how things are working. I want to know how nature functions, I want to know how biology works, and in order to understand that, most of my research is using computer simulation, where we can literally simulate a biological process and from there extract insights into the inner workings of these proteins. In addition, I'm interested in controlling chemistry with light. I mean, that's a topic which will become very important in the years to come, because we want to be able to efficiently utilize sunlight as a source of energy for our society. And what we are exploring is how we can increase the interaction between light and matter, because that would help us to increase a lot the efficiency with which we can harvest the energy from the sun. To do that, we use both theory and experiment. And in the theory, well, as it implies, we try to understand how light and matter interact and what is happening when we increase that interaction. Experimentally, we try to then do the same, to try to confirm or at least to falsify what we predict theoretically. And what we do to increase the light is we actually put our sample with which we want the light to interact, we place it in between two very tiny mirrors to get samples like this. So you see a small plate, in between is material that can absorb light, around it on both sides are silver mirrors, yeah, they look nice and reflective, and these mirrors, they literally can trap the light in between. So the material inside interacts much stronger with the light which is trapped, which cannot go out, than if it would not have the mirrors around it. And well, we use this setup that you can see here to actually explore what happens. We can spectroscopically, that means with light, interrogate our samples to understand how putting the mirrors around our sample affects the material inside. So a typical working day for me here in the university starts in the morning when I discuss with my team members the progress of their projects. We discuss the interpretation of the data, and we discuss and we plan the next steps. During term, when I'm teaching, the next step for me is to prepare the classes or to actually teach classes, but of course that is only when students are studying. During my day, I think I drink a bit too much coffee, but I really like the coffee breaks, because during coffee breaks I have the opportunity to talk to my colleagues who do different things. I'm interested in what they're doing, and these discussions very often lead to new ideas or solutions to problems that we will run into, and often even completely new projects. Plus, I just enjoy hearing what the others are doing. After lunch, that is usually the time I have for myself. I spend that mostly writing manuscripts about the results we have obtained in order to share them with the community, or I review manuscripts that colleagues of mine from other universities want to share with the community, and that needs some kind of a quality check. My own research, during the day I hardly have time for that, but I tend to do that in the evenings. And I enjoy doing that because I have some hours in which I can actually do something I find interesting, and that makes my job nice because I don't really need an additional hobby to do next to it. Thanks for watching our videos.
We hope you like it.
If you'd like to know more about our research,
Join the Researchers' Night.